Welcome back to the deep dive. We all know large language models are, well, pretty amazing. They can summarize complex texts, generate code, write stories. They're masters of that fuzzy, probabilistic world of human language. But here's the thing, where they really hit a snag is with absolute logical precision.
Exactly.
When you get into that unforgiving, deterministic world of formal logic, where you can't just sort of guess a result and hope it's valid, well, LLMs often fall short. So our mission today is a deep dive into this framework called PDDL-INSTRUCT. It's a really targeted approach, almost like teaching LLMs the formal rules needed for automated symbolic planning, basically turning them into reliable digital engineers.
Yeah, and what we're fundamentally tackling here is what some call the impedance mismatch. It's a core conflict.
Impedance mismatch.
LLMs are built on statistical patterns, right? They figure out the most likely next word or the most probable sequence of actions based on tons of data.
Right, probabilistic.
But symbolic planning, that needs you to track deterministic state changes over potentially very long sequences, step-by-step certainty. Think of it maybe like an LLM writing a really long, complex contract. It can generate clauses that sound right, plausible language. But it doesn't have a built-in checker to see if Clause 5 totally contradicts a definition laid out way back in Clause 1.
I see. It loses track of the internal consistency.
Precisely. And in planning, if your model messes up the state tracking at, say, step 3, well, every single step after that, which relies on that wrong state, is logically invalid. The whole plan collapses. LLMs just aren't inherently good at maintaining that kind of long-term logical consistency or reliably fixing their own complex mistakes when they do go wrong.
Okay, so if the LLM is the language expert, we're basically handing it a strict grammar book for reality itself. Before we jump into the solution, PDDL-INSTRUCT, maybe we should unpack that rulebook. What exactly are we teaching the AI? What are these planning fundamentals?
Good idea.
Yeah.
We need to cover the basics of classical planning. So a planning problem is formally defined by a few key things. First up, you have fluents, or sometimes called predicates.
Fluents or predicates, right.
These are like tiny atomic statements about the world state. Things like on block A, block B, or maybe hand empty. They're either true or false at any point in time. Simple facts.
Okay, like variables describing the situation.
Exactly. Then you have the dynamic part.
Mm-hmm.
The actions. These define how the state can actually change. And they're typically defined using something called the strips formalism.
Strips.
Yeah, it just means each action is defined by 3 specific sets of these fluents. First, preconditions what absolutely must be true before you can even try the action.
Makes sense.
Second, add affects the fluents that become true after you perform the action. And third, delete affects the fluents that become false after the action.
Wait a sec, that's where my engineering side perks up. Why do we need both add and explicitly delete effects? Can't the system just assume that whatever isn't added stays the same? Or, infer the deletion?
That's a really insightful question. It gets right to the core of why this deterministic tracking is so crucial and, well, difficult for standard LLMs. You need the delete effects because the planner, or the LLM in this case, has to explicitly and unambiguously show the change to the current state.
Okay.
So for instance, if you move block A off of block B, you absolutely must delete the fluent on block A, block B. If you didn't, the system might erroneously think block A is now magically in 2 places at once, its new location, and still on B.
Right. No ambiguity allowed.
None. It forces the model to track the precise consequences of every single action. You can't just hand-wave it.
Got it. Precision is key. And the language for defining all this is PDDL, the Planning Domain Definition language. So using that classic blocks world example, stacking blocks, you usually need 2 files to set things up, don't you?
That's right. 2 files.
The first one is the domain file. This is like the physics engine for this little block universe. It defines all the reusable rules, the types of things that exist, the predicates like hand empty or clear, and the general action templates, the schemas like stack or unstack. It's the laws of this world.
Exactly, the physics. And the second file is the problem file. This sets up a specific scenario within those laws. It defines the actual objects you're working with, say blocks A, B, and C. It specifies the exact starting state, the .init section, listing all the fluents that are true initially. And crucially, it defines the goal state, the .goal, like maybe getting a specific tower built on AB and on BC.
Okay, so the domain is the general rules, the problem is a specific task. And the LLM's job is to generate a sequence of actions using the schemas from the domain that are valid at every step and transform the initial state into that goal state.
Precisely. Respecting the rules, step by step.
Right. So the big leap here is PDDL-INSTRUCT. It's moving beyond just, asking the LLM for a plan and instead actively teaching it how to reason formally. But hang on. Isn't all fine-tuning technically teaching? How is this logical chain of thought approach really different from the standard CoT we hear about all the time? Are we just giving it a super specific format?
That's a really important distinction to make. This isn't just a soft prompt like, hey, think step by step. This logical code is formally constrained. The LLM isn't just encouraged to show its thinking, it must output its reasoning in a very specific, structured, formal sequence for every single action step.
Exactly. So it's not just a suggestion, it's a requirement of the output format.
Exactly. The structure itself is the key. It makes the whole process auditable. The model literally has to generate tokens saying something like, okay, executing action pickup block A, precondition check. Is hand empty true? Yes. Is clear A true? Yes. Okay, applying effects, add effect, holding A, delete effects, hand empty, clear A, new state is now S.
Wow. Okay. That sounds incredibly meticulous,
Yeah.
almost laborious for the LLM. It has to generate all this extra logical scaffolding around every single action. Does that mean the training time or even just the inference time goes up significantly because you're forcing this very verbose, structured output?
It is definitely more computationally intensive, yes, both in training and inference. But that extra cost is precisely the trade-off you make to get reliability. The crucial part, why it matters so much, is that this structured output transforms the model's internal, often opaque reasoning process, that sort of probabilistic black box we talked about, into something transparent, verifiable.
A transparent artifact.
Yeah, and once you have that transparent logical sequence, you can objectively check it against the formal PDDL rules. That verifiability is the absolute key to providing targeted, effective, corrective feedback during training.
Okay, that makes sense. You need to see the working to correct the mistakes properly.
Exactly. And to teach this kind of logical rigor, the researchers designed this really interesting two-phase curriculum. Think of it like school.
Okay, phase one.
Phase one is like the textbook phase. This involves initial instruction tuning. But here's the clever bit. The dataset contains both correct plans and deliberately incorrect plans with explanations of the errors.
Ah, so it sees failures too.
Yes, it learns to recognize and even articulate common logical mistakes. It's like a student studying worked examples in a textbook. You see the right way, but you also study common pitfalls, common errors, so you learn to spot them. It builds an intuition for why an action might be invalid before it even tries to generate its own plan.
Okay, building foundational knowledge, recognizing patterns of error. Then what's phase two?
Phase two is where the real innovation kicks in, the tutoring phase. This is where they implement this iterative feedback loop. The LLM generates a plan, including its detailed logical CoT reasoning.
Right, that's showing all its work.
And then this whole trace, the reasoning and the proposed plan, gets passed to an external checker, specifically a standard traditional symbolic planning tool called VAL, validator.
VAL. Okay, so this isn't another neural network?
No, absolutely not. VAL is a classic deterministic symbolic tool. It's been used in the planning community for ages. Think of it as the incorruptible oracle in this system. It represents objective, logical truth according to the PDDL rules.
The ground truth checker.
Precisely. VAL systematically goes through the LLM's reasoning. It looks at the state the LLM claimed was current before an action, and it verifies. Were the preconditions actually met in that state according to the rules? Then it looks at the state the LLM claimed resulted after the action. Was it updated correctly based only on the defined add and delete effects?
And if the LLM messed up?
If VAL finds an error, a precondition violation, an incorrect effect application, and provides specific objective feedback, like error at step 5, precondition, clear block C, was false in state S4. This concrete, detailed feedback is then integrated back into the training data for the LM.
So it's not just wrong plan, it's wrong plan here for this specific logical reason.
Exactly. It forces the LLM to confront and correct its specific flawed reasoning based on an objective external source, not just try randomly again.
And this structure, this is that neuro-symbolic pattern we keep hearing about, right? It seems like the best of both worlds approach that's emerging for trustworthy AI.
You nailed it.
The LLM, the neural part, brings the flexibility, the ability to generate complex, plausible reasoning chains.
And VAL, the symbolic component, brings the rigid mathematical guarantee of logical soundness, the proof.
This hybrid approach really does seem like the blueprint for making AI reliable in situations where just being probably right isn't good enough.
It really is. It stops the LLM from just getting stuck in its own hallucinated world, where things might seem internally consistent to it, but are actually violating the ground rules.
Okay, let's talk results then, because
Yeah.
the proof is in the pudding, and the numbers they reported seem, well, staggering.
Yeah.
Using this plan bench evaluation suite, the Llama 38B model, which is a pretty capable model, its accuracy in Block's world just soared, didn't it?
It really did. The baseline, just prompting Llama 38B for a plan, got it right only about 28% of the time.
Okay, not great for logic tasks.
Not reliable at all. But
Yeah.
with the full two-phase PDDL-INSTRUCT training, that accuracy jumped to 94% in Block's world.
Wow. From 28% to 94%. That's a massive leap.
Huge. And the experiments revealed a couple of really critical insights about why it works so well. The first was about the importance of detailed feedback.
From VL, right?
Exactly. They compared giving that detailed feedback like failed at step 3 because precondition X was missing versus just giving simple binary feedback, basically just valid or invalid.
And the detailed feedback made a big difference.
A huge difference. That detailed error message acts as a much richer, higher bandwidth signal for the model to learn from. For instance, in some of the more complex planning domains, it led to accuracy gains of like 15 percentage points just from the quality of the feedback compared to simple binary feedback.
15 points is substantial.
It really is. It lets the model pinpoint exactly where its logical chain broke down and adjust accordingly rather than just flailing around. Faster credit assignment, essentially.
Okay, that makes sense. And the second big insight came from this mystery Block's world domain. That sounds like a particularly tough test. What was that about? And what did it prove?
Right. Mystery Block's World was designed as a true generalization test. What they did was take the standard Block's World setup, but obfuscate all the predicate names.
Obfuscate, you mean just rename them?
Exactly. So a familiar predicate, like on a B, might become something totally meaningless, like predicate 1AB, or clear X becomes predicate alpha X. All the semantic clues from the words on or clear or hand empty are removed.
Ah, so the model can't just rely on its understanding of English words anymore.
Precisely. An untrained LLM, or one just prompted, relies heavily on those semantic associations and its performance tanks. For Llama 3, the baseline accuracy in Mystery Block's world was, wait for it, 1%.
1%, okay. That clearly shows it was just pattern matching the words before, not understanding the logic.
Absolutely. But here's the kicker. With PDDL-INSTRUCT, Llama 3's accuracy in Mystery Block's world jumped from that 1% baseline to 64%.
64%. Even with meaningless predicate names.
Even with meaningless names. And that massive improvement is the crucial evidence. It proves the model didn't just memorize what on means in a planning context. It actually learned the formal syntax and the logical structure of PDDL actions.
It learned the rules of the game.
It learned the rules. That an action works if and only if the set of predicates listed in its precondition field are currently true in the state, regardless of what those predicates are actually called. It learned the abstract logical form.
That's genuinely impressive. It learned structure, not just semantics.
Which is exactly what you need for reliable logical reasoning.
So pulling this together, what are the main takeaways for AI engineers trying to build more reliable systems?
Well, I think there are two big ones. Takeaway 1. This neuro-symbolic pattern combining a flexible neural generator with a rigid symbolic verifier really looks like a key blueprint for building trustworthy AI, especially where correctness is critical.
Okay, the hybrid approach.
Takeaway 2. The curriculum matters. That two-phase approach, building foundational intuition first, then drilling logical rigor with targeted, verified feedback, seems way more effective than just trying to hammer logic into a model with standard monolithic fine-tuning. Teach, then tutor with verification.
Teach, then tutor. I like that. Now, even with these huge improvements, the researchers were quite upfront about the current limitations, weren't they?
Yes, absolutely. Transparency is important.
They mentioned it currently only handles satisficing planning. Can you unpack what satisficing means here?
Sure. Satisficing means the system finds a valid plan, any plan that successfully reaches the goal state following the rules. But it doesn't guarantee that plan is the best one. For instance, the shortest plan or the lowest cost plan.
Ah, okay. So it gets the job done, but maybe not efficiently.
Right, which makes this current PDDL-INSTRUCT TM framework unsuitable for tasks where optimality is critical. Think complex logistics, scheduling, or minimizing movements in industrial robotics. You often need the most efficient plan there, not just any valid one.
Gotcha. And they also pointed out limitations in the complexity of the PDDL features it supports.
Correct. It currently handles a core subset of PDDO, but it excludes more advanced features that are often needed for modeling more complex real-world scenarios. Things like conditional effects, where an action's effect depends on the state, or durative actions, actions that take time, or numerical fluence, like fuel levels or costs.
So still some way to go for full real-world complexity.
Definitely. And even with that impressive 94% accuracy in Block's world, errors still happen, especially as the problems get longer and more complex. The main failure modes that remain are incorrect effect application, basically, messing up the state update after an action,
Still struggling to track consequences accurately.
and precondition violation, trying to do something illegal based on the current state. So precisely tracking that state and applying action consequences correctly remains the core challenge, even if it's much better.
Okay, so wrapping up, what's the big picture here? It feels like PDDL-INSTRUCT is a really significant step towards making LLMs not just fluent, but actually reliable logical thinkers, right? Bridging that gap.
I think that's exactly right. It shows that this kind of formal, structured reasoning can be effectively taught to LLMs, moving them beyond just probabilistic language generation towards verifiable execution.
What's next on the horizon for this line of research?
Well, the immediate next step seems to be tackling optimal planning. Maybe by adding some kind of penalty for plan length or cost into the training process, guiding the LLM towards more efficient solutions.
Pushing beyond just valid to good.
Exactly. But the perhaps more ambitious long-term goal is to develop genuine self-verification capabilities within the LLM itself. Imagine if the model could reliably check its own logical steps without needing that external oracle, VLL.
Wow, that would be a game changer. Much faster, easier to deploy.
Definitely. Reducing that reliance on the external symbolic tool is a key goal.
Okay, so final thought for you, our listener, to chew on. Consider where else this fundamental approach, teaching formal logic, using this neuro-symbolic pattern with structured, verifiable output, could be applied. Think about other fields that desperately need auditable, trustworthy output from AI. Maybe safety-critical systems in medicine, analyzing complex financial regulations for compliance, or automating intricate industrial processes. If we can force the model to show its work in a formal, checkable way, well, that might just unlock a whole new level of dependable AI across many, many different areas.